Our next presenter is John Mailhot, who is the CTO and Director of Product Management for Imagine Communications. And he's going to talk about Interoperable JPEG-XS, which is obviously an excellent way to compress video and transport it, and working with ST2110-22 and NMOS. So take it away, John.
Okay. Great. Well, thank you all for showing up, and some of you I know and some of you I don't, but we can always say hi later. So my name's John Mailhot. We're talking about JPEG-XS, which is a new codec and all the bits and pieces you need to turn this ITU codec into an actual solution you can use to do real work. So first, let's talk about, this is what we're going to talk about. We're going to talk about what is JPEG-XS and what's 2110 and what's NMOS and how those mix together to make it useful. JPEG-XS, right? Why do we need another codec? Well, because it's a new year, right? JPEG-XS is a real standard from a real organization, ISO IEC 21122.1.2.3. And that has a meaning because it's not a proprietary thing. It's a real codec. You can buy the document for 237 Swiss francs. Sadly, it's not free. And you can implement it, and you're welcome to implement it. There are patents involved, and you have to do a licensing with the RAND entity, but they're reasonable is the true word there. It is very reasonable, the fee. So what was the goal of the JPEG-XS process? Because this process we've all followed, it's gone on for a number of years. The goal of the process, and this is from the abstract of the standard itself, is to represent images without visual loss at moderate compression rates. Now, those are all qualified statements. What do you mean without visual loss? Well, that's in the eye of the beholder. But you can choose the bit rate you run at to make it be true for you. Moderate compression rates, what does that mean? Well, typically people are running JPEG-XS somewhere between 1 and 4 bits per pixel. And that's a funny thing, so we'll talk about what bits per pixel are in a second. So this, ratios, so between 2 to 1 and 6 to 1, but could be higher. Typically, I don't know anyone who runs as high as 2 to 1 because, frankly, at about 5 to 1, it stops getting better looking. There's a rate in there that's quite good. And the key thing, JPEG-XS was not meant to be, there's different axes of good, right? So it was not about making, fewer bits and having a more complicated codec. It's the first time I've seen a standards body try to go the other direction and have a simpler codec that you had to spend maybe a few more bits. But that's what we did with JPEG-XS. So it's designed around being lightweight from a software implementation standpoint and a hardware implementation standpoint. Now, don't confuse that with easy. Like the math is kind of hard, and the code, it's a codec. You got to understand what you're doing. But from a computational footprint standpoint of how many cores does this take on a reasonable processor to encode or decode the picture, that's where JPEG-XS is optimized to be a reasonably low footprint, especially compared with JPEG 2000. So our estimation is it's at least 3 times less cores or less, FPGA gates, whichever way you want to look at it, than JPEG 2000 was. So, okay, that's JPEG-XS. Now, there's alternatives, right? So compared to JPEG 2000, like I said, it's performing about the similar rate family, especially if you compare against ultra-low latency JPEG 2000. Why? Because ultra-low latency JPEG 2000 cut the picture into stripes. What XS decided to do was to just have a moving stripe, meaning that each block row is built out of pixels that are relatively close to it above. And that size bounds the latency. So the latency of the codec itself is, I think it's about 32 lines. It's a very, crazy low amount of time. Now, you wind up having, buffering to get the image organized and buffering because of the IP networks and things. That's really the source of latency. The codec itself is the smallest contributor to the link latency. The other, the other thing, there's a lot of details about JPEG-XS and performance curves and all this stuff. There have been talks about JPEG-XS at like every show for a while. So if you look online, you'll find all kinds of talks from the guys at Intipix and other places about JPEG-XS. So I'm not going to try and go into the science of it here. It's been really well covered in other talks. So how many bits is this really? Because bits per pixel is hard to get your head around. So pick your favorite video format. We're in the US, so we'll talk about 1080i 59. On 1080i 59, 1 bit per pixel is like 108 megabits. You do the math, it's, 20 bits per pixel is uncompressed. All right, so 1 bit per pixel is like 108, or 1080i 59, sorry, it's 65 bits per pixel. I can't even read my own chart. And the 1080i, if you run it more like 2.5 bits per pixel, which is kind of a nice, pretty good contribution length, to be honest, that runs about 150, 160 bits per megabits. If you went crazy and went all the way to 4 bits per pixel, that clocks in at 260. Most people run at either 3 or 2.5 for contribution purpose. That seems to be the locus of opinion, is somewhere in there, just under 200 megabits for 1080i. Twice that for 1080p, 4 times that for UHD. So that's how these bits per pixel translate into actual bits you pay for. And this table will be in the chart, the stuff online afterward. But this is really just math. 20 bits per pixel is uncompressed, and then for 422 10-bit. And then all these other things just divide down from there. There's about a 5% overhead on top of the raw, calculated out from the pixels to account for all the IP packing overheads and everything. So these are numbers that include that 5% overhead from IP encapsulation. Okay, so that gets you a bit stream, but that gets you a set of bits. How do you deliver those bits? So in most people now, we're mapping the JPEG-XS bit stream into SMPTE 2110-22. Now 2110-22 says how the timestamps and timing of the video bit stream interact with all the other parts of 2110. And that's important, right? Because you need a timing model to know how to line up all the parts, because you still have audio and ANTS data, and you better have a timestamping methodology of how those fit together later. So the IETF, remember them, the IETF, they developed separately an RTP payload spec. So the RTP spec from IETF says how to map the JPEG-XS bits into RTP packets. And then 2110-22 supplies some requirements on top of those RTP packets about their timestamps and how they're advertised and some of the fields that have to be in the SDP. So these standards all exist, and it's a matter of using them and reading them and thinking them through correctly. So that's cool, but how do I switch it? Like, can I use NMOS with this? Because remember, AMWA NMOS, is really good for controlling 2110 things. Sure enough, in AMWA, best current practice document, BCP 006-01, that says exactly how to do JPEG-XS in NMOS. And that's, I think, draft right now, but it's all but finished. There's a few PRs that are getting tweaked up. And it's really not complicated. It's done in the simplest way that was reasonable. So if you're familiar with SDP files, I'm sorry for you. But if you're familiar with SDP files, you'll see in the JPEG-XS one, lo and behold, it says JXSV, JXS video. Couldn't be clearer. There's a couple of new parameters for packet mode and level. And in 2110, it actually requires you to list the bit rate in the SDP, which is a pretty handy thing, really. And so this particular thing was 274,000 kilobits, because that number's in kilobits. So there you go. So you can use NMOS ISO 5 to switch these signals, and that's a good thing, because then we don't have to write in our control system, an API driver to some other thing to learn how to switch JPEG-XS. It'll just work. So, well, that's all good, right? So there's SMPTE, there's AMWA, there's IETF, there's all these organizations that have written piece part documents about this JPEG-XS stuff. Now, separately from all that, if you remember back to JPEG 2000, there was a common practice of using transport stream for JPEG 2000. And so there was a set of people who said, yeah, you know, we should probably have an updated spec of that works for JPEG-XS. So over in the Video Services Forum, another organization, we wrote a document that describes how do you do JPEG-XS inside an MPEG-2 transport stream. And again, it has pointers to, there's an MPEG document that says how you map that to that, and there's another MPEG document extension for the transport stream itself to have the right little magic bits that say JPEG 2000 is type 37 or whatever it is. So this is all wrapped up in this VSF spec, TR07. And there's people who've implemented that around the show floor, and they've had an interop event and traded files, and so that's gone along well. In TR07, we also defined some capability sets, because the idea is you as an end customer could say, I need an encoder for JPEG-XS, I'm going to do TR07 mapping because of some application requirement, and I need it to do HD. And so you can say, VSF TR07 capability set A, and that's a spec, and you can put that in your purchase rec, and vendors either comply or they don't. It's straightforward, instead of you having to document all the little piece parts that they have to comply to. In the same way, there's a capability set B for UHD1. You'll recall that what we call UHD is really UHD1, 4K. There's also UHD2 for 8K, and yes, people are doing UHD2. More in Japan and China than here, but don't worry, it'll come along just about the time we get UHD figured out. So TR07 defines these capability sets. Oh, by the way, these VSF specs are free, and they're available online. And if that link doesn't work, you can yell at Bob Roll. No, don't do that. Now, back to the other thread, though. What about the 2110-22 case? Because again, we talked about, well, there's an AMWA thing and a VSF thing and a this and an ITU doc and a IETF document. Wouldn't it be nice if there was a single spec that said all those parts and all the constraints in one document, so you can just point to it in your bid spec and say, do that. That's TR08. So TR08 has, pointers to the JPEG spec, the SMPTE spec, the AMWA spec, and the written by the VSF, and also the IETF. I couldn't fit, I was running out of space. So it says, use JPEG-XS, use it in a constrained way, because JPEG-XS has a lot of features that you could use, but you can make a simpler implementation if you maybe don't use some of the really exotic features. So we said, well, use JPEG-XS, but constrain it, because some of the features just don't belong in the television contribution use case. Use the RFC, use it correctly. Also constrain it by the constraints from SMPTE 2110-22. By the way, here's how you should do the audio. Here's how you should do the VANCE data, because those are an important part of the contribution, right? If those don't work, it's not useful to have video without audio. And then we also defined capability sets in TR08, like TR07, but they're a little more complicated and interesting. And importantly, we defined a table of interoperability formats. Now, you'd think this goes without saying, but it's useful if there's a table that says, by the way, I tested against the things in the table. And the things in the table are the stuff people use every day, 1080i, 1080p, 50, 59, So it's nice to have a table because it gives your test people something to test against. So what are these capability sets in TR08? Well, we said there's 3 levels, HD, UHD1, UHD2, just like we had in the other document. But we also had some use cases, so capability sets and conformance levels. So the levels are how big a picture and how high a frame rate as well. And then the capability sets are based around use cases. So the intra-facility use case is designed for, if I was running inside my own plant, just, within my 4 walls. So timing recovery is synchronous, which is the interesting one. 16 channels audio, 1080p, whatever. Then there's an inter-facility, meaning like links between my facility and yours. Well, in that one, it's super important that things support some kind of asynchronous recovery, because, you know, even if I tell you, you know, I'm PTP locked to traceable to GPS, and I know you are too, and as a facility designer, you would never ever trust that. You would always sync the signal at your end anyway. So we said, well, look, you know, that use case, we're going to build in that it's just a requirement to receive asynchronous signals correctly. Then there's a whole nother activity going on called IPMX that's about enterprise systems and using JPEG-XS in some enterprise environments, but it has a little bit different set of requirements. So they want to have asynchronous capability, also have a slightly different timing model than 2110, so there's an IPMX timing model. I think it's in the end going to be exactly the same as the 2110 timing model, but they haven't quite finished deciding that. And then there's a IPMX Plus capability set, which is really, if you think about their use cases, they're much more worried about the multimedia formats and typical computer formats, whereas these two are really built around television formats. So in the last one, they've added in the 444 formats and up to 12-bit and up to 1200 vertical, because a lot of monitors you buy are actually 1900 by 1200 or 1920 by 1200. So they want to be able to carry those. But of course, in the television world, that's just not a typical format. So there's different thought running into which applications go with each of those use cases. And again, the goal of the document, TR08, was to write it down so that as an end customer, you could say, look, I'm doing contribution links for sports or whatever. I need B, and I'm going to do UHD, so I need UHD1 interfacility. And that way, the requirements are written down. You can make one reference to a spec, and the vendors know what you mean because it's written down very thoroughly. Now, this spec was developed by a committee within the VSF. It was chaired by John Dale, who is, I think, our next speaker. And many of us participated in it every couple weeks. And so it's, well understood by all the vendors in the industry, because, frankly, all the vendors that were involved in doing JPEG-XS work participated in the committee and went and made it happen. Now, this, of course, like I said, ties into the other IPMX work for those use cases. So that's how to do JPEG-XS in an interoperable way. Now, I don't have a slide about it, but recently there was an interoperation event in person. I know, shocking that seems. It was actually hosted by Amazon Studios in Los Angeles, and we had 11 different vendors there, and things went really well. We all separately had developed to TR08. We had actually done some PCAP exchanges, so we would capture, streams and give them to each other and trade, up ahead. But, push comes to shove when you actually hook it up for real in a, in a lab with a switch. And I'd say, 90% of the from and to just worked, and the others had pretty minor issues to work through. So this actually went better than some, like the first JPEG 2000 interop wasn't nearly as good. Are there any questions about JPEG-XS and how it works and who should use it and why? And
do you really have any idea of the feasibility of inter-facility JPEG-XS over 2110-22 compared to TR07? One of the main things that we see for the use case for JPEG-XS is for sports contribution, right? And in lots of places, if you're a sports provider, you don't necessarily have the potentiality to put an NMOS controller in each of your stadiums where you're actually trying to transmit JPEG-XS. So how would you go at solving that? Or would you just switch back to basically TR07?
So in most cases, we've seen the links between places, like the interfacility links, are actually set up as unicast anyway. So you set them up as fixed unicast links, which is roughly what you would do with TR07 either, is you just put in, unicast transmit, and then it's at the edge device at the, wherever it's going to, it does a hard receive, and then you either decodes it and presents it as SDI, decodes it and presents it as 2110-20. But you're right, on the WAN, there's not currently a common practice of using something like NMOS in the wide area. Now, there is work going on in the VSF about that. I don't know if there's a talk about that this week. There probably is. There was. And that's actually covered in VSF Tier 09, which says how to advertise enough technical details to do wide area transactional work between really arm's length parties using NMOS as part of the control strategy, and then either GRE tunnels or not to consolidate the essence flows. But the value of being able to have the flexibility of essence flows that you get in 2110 is pretty significant. And when it's unicast, the fact that you don't have like a big giant NMOS environment, that's okay, because again, the wide area network doesn't want to hear from multicast anyway.
Okay, so if you're interested in JPEG-XS, I encourage you to stick around for our next presentation.